Hi, this is Daxian Chuang from Northeastern University. I'm very glad to participate in the MIT A&B Applied Energy Symposium and introduce my work through the video. Today my topic is stable Thiophosphate-based all-solid-state lithium batteries through conformally interfacial nanocoating. My advisor is Professor Hongli Zhu. In the beginning, I will have brief introduction on my work. Lithium batteries have been widely applied in portable electronics because of their high energy density and long cycle life. These years, its application has extended to some large-scale devices like the very popular electric vehicles. For further improvement, uh, we need the lithium battery with higher energy density and power density to comparable with the combustion engine. However, the frequently reported self-combustion or explosion safety concern is a huge problem, hindering the further application of lithium batteries. The safety problem is rooted in the employment of flammable organic liquid electrolyte and high voltage cathode. Therefore, replacing the flammable organic liquid electrolyte with non-flammable solid-state electrolyte can intrinsically solve this problem. As shown in this image, solid-state batteries exhibit higher energy and power density than conventional lithium-ion batteries. Solid-state electrolytes have been widely studied for a long time. Based on their composition, they can be classified into ceramic, polymer, and their composites. In the past, solid-state electrolytes are limited by their lower ionic conductivities, which is lower than 0.1 millisiemens per centimeter, while organic liquid electrolyte exhibits a much higher ionic conductivity of 10 millisiemens per centimeter. Among these candidates, sulfide electrolyte is one of the most popular ceramic electrolytes, which has comparable ionic conductivity with liquid electrolyte. This advantage renders sulfide electrolyte based on solid-state batteries working at room temperature without sacrificing performance. In comparison, other electrolytes like the oxide and the polymer, they still need external heating to achieve a considerable performance. As to the energy density, electrodes include cathode and anode play most important role. Based on the calculation, the development of cathode with high working voltage and anode with low reduction potential can highly increase energy density for the cathode, such as this layered transition metal oxide can work at high voltage higher than 4 volts. Lithium metal, which is the ideal anode for lithium batteries due to its ultra-high capacity and lowest reduction potential. It is a great chance to match this cathode and anode with sulfide electrolyte to achieve a high energy density and high safe batteries. However, sulfide electrolyte suffered from rather narrow electrochemical stability window, which means they will be reduced or oxidized during electrochemical reaction if the working voltage over the stability window. For example, LGPS, which has an ultra-high ionic conductivity of uh, 10 millisiemens per centimeter. However, its electrochemical stability window is only range from 1.7 to 2.1 volts. When worked at high voltage, it will be oxidized into sulfur and some polysulfides. When worked at low temperature, when worked at low voltage, it will be reduced into some lithium sulfide and other polysulfides and other species. This decomposition will consume the electrolyte and bring huge resistance into batteries. Another big challenge is the chemical stability of sulfide electrolyte against high voltage transition metal cathode and lithium metal anode. The reaction energy between various cathode and sulfide electrolyte is much higher than with other electrolytes. To solve this problem, it is necessary to insulate the cathode with sulfide electrolyte. Many works have proved that the reaction between sulfide electrolyte and lithium metal is also very drastic. Here, I will introduce my work. It was published in Nanoletters. In this work, we focused on the stabilization in cathode part. As illustrated in this schematic, we applied an interface nanocoating on NMC cathode. The coating material is shortened as LLSTO, and the sulfide electrolyte is lithium sulfide, lithium phosphorus sulfide chloride. To avoid this side reaction between sulfide electrolyte and lithium metal, we use lithium indium as anode. The fundamental mechanism for interface stabilization is illustrated in this schematic. For bare NMC, there are severe chemical reaction when directly contact with electrolyte. Meanwhile, during first cycle, there are electrochemical reaction exists due to the electron conduction at the interface. As a result, both NMC and the electrolyte will decompose, and the interface resistance is highly improved due to the low ionic conductivity of decomposed products. However, when we coated a thin layer of LS2 on NMC, NMC was insulated with the sulfide electrolyte, which avoids the chemical reaction. More importantly, the LS2 layers enable high ionic conductivity and electron insulation, which avoid the electrochemical decomposition of electrolyte and much decreased interface resistance. Here we show the wet chemical coating process to prepare this thin layer coating. Bare NMC was mixed with the precursors of LS2. After the gel-formed process, all the NMC powders are collected and sintered in air. As a result, they are conformally coating on the surface of NMC. As this is the ICM image, we can see LS2 is uniformly coated on the NMC. And from the showing the EDS mapping, LS2 is uniformly coated on the NMC particles, and the thickness is around 20 nanometer. Analysis the electrochemical stability window of our electrolyte. We conducted an in situ Raman to test the stability window. The setup was shown here. There is an optical window which allows the laser to transmit and allowed the Raman signal to be collected. When run a CV test, we can find obvious oxidization peaks appeared in the first cycles, and the decomposition products is stable in this voltage because they are only because oxidization only happened in the first cycle. Through the in situ Raman, we can see in the beginning all the peaks, PS4 peaks belongs to our electrolyte gradually disappeared, and there are some peaks and newborn peaks appear, which can be contributed to the lithium sulfide and sulfur. Through the in situ Raman, we further confirmed the electrochemical stability window of our electrolyte. After that, we assembled the cathode and the electrolyte in 4-cell to evaluate the electrochemical performance. In bare NMC, we can find the initial capacity, initial charge voltage is higher than NMC with coating, and after one cycle, there are obvious overpotential exists, but in NMC with coating, there are no overpotential after one cycle, which proved there are severe reaction between NMC and electrolyte. We compared the impedance of both cells before and after one cycle. So we can find after one cycle, NMC with coating exhibits much smaller charge transfer impedance. ITT was then performed to compare the ion diffusivity in both cathodes. It is obvious NMC with coating behaves a much higher capacity, around 156 billion hour per gram, which is close to the theoretical capacity. We can get the ion diffusion coefficient with the coating of L2. The ion diffusivity was greatly enhanced. After that, we test the cycling performance in different mass loading and the rate performance. It is obvious NMC with coating exhibits a higher capacity and stable cycling and better rate performance. After 850 cycles, the capacity still retained at around 100 milliamp hour per gram. When we further increase the mass loading to 20 milligram per centimeter square, the performance is still very stable. The good performance was contributed to the stabilized interface. Finally, we did a theoretical analysis to study the electrochemical stability window of our electrolyte. From the simulated result, the window is around 1.72 to 2.34 volts, which is consistent with our experiment result. Meanwhile, the reaction energy between NMC with our electrolyte and NMC with the coating and our electrolyte with coating were also calculated. There are severe reaction energy between NMC and the electrolyte, while the other two interfaces are much stable. In the end, I will acknowledge my advisor, Professor Hongli Zhu, and other lab members, and our collaborators, and some fundings. Thank you. If you have any questions, please feel free to contact me through email. Thank you.